Hello, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellyn, Illinois. And this video is going to take a look at x86 assembly language and some for loops and while loops and tying it all together with a function call at the end. So for the class I'm teaching, this is basically chapter 6 style stuff with the loop structures and that sort of thing. So that's what we're going for here. So my first example, we're going to do 3 here, is something like this, where I'm going to be printing out basically values of 1 through 10 using I as my variable. So I just, this is very simple stuff compared to like some of the ways these things get. So I equals 1 is my initialization, I is less than or equal to 10 is my conditional statement, plus I is my incrementing, and my code is relatively simple as well. So my code is going to be over here on the left hand side. So how to attach them, how do I approach this kind of problem? I can start with the kind of the boring stuff at the end here. Call CRLF for carriage return line feed, and then call wait message. And just to prove this is working for me, okay, here we go. There's my carriage return line feed, and there's my wait message. So far so good. So got that stuff out of the way. So I can set up my variable for I can use int. I can't use int. I have to use I sign double word 1 to start, because I'm starting. Int is a signed double word, and I is its name, and 1 is its initial value. And so whenever I do this kind of stuff here with a loop, there's 2 things I got to do. I have to come back around, right? A for loop, a while loop, all it really is a repeated if statement. So when it comes to that, that's all there is to it. If you think of flow charting for our classes, think about CIS 1400 or that sort of thing. An if statement, the arrow just keeps on going down. Like it just keep on, but for a for loop or a while loop, that arrow when it comes back around. So you have to just think of that way. So I have to have that, and then I have to have a way out, which is basically a jump out. So I have to have basically 2 labels for a for loop or 2 labels for a while loop. And so the first thing I do here, since I've already done the initialization up top here as part of the data, is, or even if you want to just kind of do it this way, put a question mark there and just say, okay, let's move into the I register, the I variable 01. You want to play it that way too, just to kind of feel that way. There's my initialization of I, and I want to make sure that's done outside of the loop, because if I come back around, it'll basically infinite loop on me if I'm resetting it every single time. So my next step, what's my conditional statement? So you have to think of this thing in the reverse order. If I is less than or equal to 10, what is that? That is what keeps me in the loop. But what gets me out of the loop is making that a false statement. And what makes that false is turning the less than and equal to into a greater than. So if I would go ahead and compare I to 10, and if I would jump if greater than to done, that would take care of that. And so keeping on going here, I have to make sure, this is all the things you have to do yourself here, I'm going to make sure I do my loop. Because if I forget this, just like basically this jump is the only difference between an if statement and a loop. Because if I forget this jump to go back and do it again, it's just going to fall through, and it's an if statement. So if you want to think of it, that one tiny line of code is the only difference between if and for when it comes to this kind of stuff. So let's just do the code real fast here. Let me print out, let's see, so move into the EAX register the I, call write int. Move into the AL register the space, call write char, and let's see what happens. What I was expecting here. So the last step, it is printing, and it's non-stop churning out +1, +1, +1. So it's infinite looping. And that's because this ++I is not being implemented in my code. So there's so many little things, right? Here's my conditional statement. Here's the code itself. And then again, the final thing you do, and it's kind of a misnomer here in for loop because it feels like it should be, where does it go? It's actually the last line of code before the unconditional jump back. So if I increment I and run this one more time, now you will see 1 through 10, and it's printing out correctly because it's starting with 1, makes it through, falls through, so it's perfectly legit, prints out the 1 in the space, increments I, and goes again. And so this is completely different than the loop operator, or the loop operation. And so just be aware of that for this kind of thing, you kind of can't really use that loop operation anymore. So this pretty much covers step 1. So I want to go back and cover step 2. So let's take a look at the next slide. Okay, so this is a different problem I want to do. So I say, okay, for loop, while loop, int I equals 0, while I is less than or equal to 8, print, oh boy, what does this mean? And we'll get there, and then increment and print out. So there's a lot of commonality here between this and the previous example. But this is the only line of code that kind of screams at you, what the heck is going on? Because this is, in this case, this is an operator, like an operator overload for the cout object. So this is, you know, stream on the left-hand side, value on the right-hand side. So this calls a print statement. However, this is the bit shifting operation, right? So this takes 1 and it will bit shift it I times. And so we're going to see that this example, there's a pretty interesting example, something I actually learned myself here that I didn't know until about 10 minutes ago when I tried to do this for the first time and had to restart my video. So when I is 0, we shift 1 over 0 times and we'll get 1. And then if I do it 1 time, I'll get 2 and 4 and 8 and 16. And you can see down here, this is our output. This is what we're expecting to see. So let's see, I can get rid of some of this stuff just to kind of just to do it again and just to kind of get used to doing this. I'll leave the CRLF and the wait message in here. But again, same deal. I need something to loop back around and I need something to say, oh, I'm done with everything. And so, and then coming back again, this time the I is going to be set again to, oops, sorry, move I to 0 this time. And so I'm setting I to 0, and now I come again, and so now the first check is that conditional statement one more time. Compare I to 8, and what kicks me out of this is the opposite of less than or equal to. It's greater than again, and then otherwise done. And then remember the unconditional jump back to again. And then we'll see about this other stuff too. So, and then I guess right now I can just print out, move into the EAX register. Just for the moment, I call write int, and we're going to play with this in a second here. Move AL, and then move the space character and call write character, and run this out. Oops, and that infinite loops a +0 because I did not do the final step here, and I did not increment my I. Okay, so what you see here now in this step, I'm supposed to be getting 1, 2, 4, 8, 16, and so forth, but I'm getting 0, 1, 2, 3, 4, 5, 6, 7, 8. So I'm not getting the powers of 2, but I'm getting I, which is fine, right? I mean, this is a good first stepping stone. I know I'm making progress toward the solution to this problem. So now it comes down to, how do I work this line of code? And so if I wanted to, I could, instead of moving I into this thing, I could move 1 into it. And then I could try to do something like this, a shift left, and I say shift left EAX, and I say I. And like, that totally makes sense, right? Move 1 into EAX, and then try to shift it over I times. But when you build this, and again, I did not realize this, I never had this come up before, you get the error invalid instruction operands. And you're like, well, what's wrong with this? And so I looked it up. And so here we go. So here is from some web page somewhere, but documentation-wise, and I go, that's not going to fly. All the different ways that I can supply a shift left operation, 1, 2, 3, 4, 5, 6, 7, 8 different ways that I can do this with 8 different opcodes. None of them allows me to do this in this manner, which is like, that's a shame, right? So what I have to do, coming back one more time, is the one I want to use is something like this. I have a 32-bit operand that I want to shift over, but I want to shift it over a register number of times because I can't use an immediate value because that immediate value is going to change every time through the loop. And so I can actually use, the only thing I can use is this CL register. So it's kind of a workaround, but it's just the way it goes. I mean, I want to move into the CL register my I. And let's see what that does. And then I can say move shift left EAX CL times, and what does that do? I still get an error, and this one says, okay, instruction operands must be the same size, and so one way or another I have to make sure, because I is a double word and CL is a byte, so I basically can turn this into a byte pointer, and I can only make this work because this is in little endian order and because I know that that first byte is going to hold the actual value that I'm looking for. On a different architecture, this might not work, but for x86 architecture, yes, it will work. And so there are my values, 1, 2, 4, 8, 16, 32, all the way up to 256. So kind of, I'm saying that's the byte pointer is a hack because this won't work on all systems. So, but if I did do something like this, and I can just, instead of using an int for this thing, if I just used a byte, because that's what we're trying for. And so you're never going to shift anything over more than 32 times. So you're never going to need anything more than a byte, at least for the next however many years until we have 512-bit computing. But there you go. So that fixes that up. So then I'm moving my I, which is a byte value, into the CL register, which then can be used to shift left the EAX register. And so then this perfectly is, this works out perfectly for what we're trying to do. So again, I learned a little something. Hopefully you did on that example too. So one more example left to do, something a little more complicated. And so this one here, linear search, right? So if you need to understand what linear search is, this might not be the demonstration for you because you need to understand arrays, you need to understand this and that and everything else. So I have a simple linear search algorithm, return the index value of whatever value I'm looking for. Is it in there? Yes or no? And if it does find it, give me the index value. And if you can't, give me a -1. That's all I'm trying to do here. And I just set up two different functions here, two different function calls to prove, and you should get 5 for the first one and a -1 for the second, because the 1 is at the 0, 1, 2, 3, 4, 5th element, and then the 11 is at element can't be found, so that should be a -1. So that's what we're going to go for, and this is a little more complicated because it's using a function, it's using parameter passing, it's using a loop, it's using all sorts of crazy stuff here. And this is, at least in the moment here, my first try at this. So let's see what happens. And okay, so how would I call this kind of thing? Like, how would I set this code up? If I have my function, like, oh my goodness here, right? Like, what am I trying to do? I'm going to just say, I'm going to put in the EDX register the offset of the array. I need a pointer, because that's what the array notation basically indicates, that I have a pointer to a contiguous block of memory. And so I'm going to use offset of array, and I've got to make sure I say it's an integer array. I'd say 32-bit integer array, because that's what an int is 32-bit. Okay, fine, fair enough. I'll need to pass along the size, and I guess I could put into ECX for now here. So, and I need to know the size, because if I'm passing a generic pointer from main into this function, there's no way to find out what the size, how many elements there are. So I'm going to have to do that myself here. And so, excuse me, so I use 7 down here, but I'm going to have to pass that in. So I'll just say size. And then I'm also going to need to pass in another element here, which is the value I'm trying to find. And that is a size. These are all int values, so they're all 32-bit ints. Okay, and then the return value is going to be going into EAX. So there's the return value, and that should either be the -1 or the positive whatever value it finds. So how would I do this? How would I do this down here just to kind of get going? If I moved into the EDX register, the offset of, oh, I don't have it yet, my array A, I can set this up here, A, signed double word, and then go 2, 9, 3, 4, 8, 1, 5. Now that should work. Get me the pointer of this array, put it into the EDX register. Move into the ECX register 7, because that's the size, just like you see down in the code over there. And then the value I'm trying to search for is make sure I do this right, EBX, and I'm searching for the 1. And then I would call the linear search function, which I have not created yet. So I can just, for the moment here, just kind of get that going here, linear search. Proc, ret, linear search, NP, just to kind of have something, and then the EAX register will return something eventually. And just for the sake of this, just to kind of test everything out and make sure we got everything going, I'll just move a 0 into the EAX register, and then down here I can call my write int, and then I can call my CRLF for carriage return line feed. And then basically do this all one more time. So this time I'm passing in A, the offset of A, I'm passing in 7, but this time I'm searching for an 11. Call linear search, call write int, call carriage return line feed. So if I did everything right, there we go. At least for the moment, I can see my +0, my +0, which indicates that everything was working out, and now I just have to fix up everything else because I'm getting into the function, I'm passing the parameters along as registers like I'm supposed to, and now I'm changing EAX to 0, returning back, and then I'm printing out that 0. So my main is essentially done, and now it's just a matter of filling in the gaps. And this is where things get interesting, to say the very least. So just to say, can't find. If I can't find a value, I'm going to move into the EAX register my -1 and return. So let's just try this out one more time. And there's my -1, -1, just to make sure that I'm using signed integers and not unsigned integers. Otherwise, this would print out a really large number, 4.29 billion something. Okay, so that can't find. That's that return -1 here. And then I'm going to have to, I know coming back here when I'm going to return, because in high-level languages, it's okay to have returns in multiple places, but there's a reason why there's a thing called a one-in, one-out principle, and it just comes back to the fact that when back in the 80s, 70s, you name it back then, way back then, that this would be so much extra code to write. And so you want to have one in, which, that's easy, and one out to every function. So whenever I do this return I, I'm going to move whatever value into I, and then I'm going to jump to done. And that's just how things are going to work here. Okay, so remember now we're going to go in here, and I need my loop. So I have it again, and I have my done, which is kind of cool, right? So if I fall through, this is what's kind of cool here. Like, if I find something, I'll jump to done. But if I go and I jump and I jump and I jump and this conditional kicks me out, it will return me to can't find it, and it'll fall through. So we'll make this thing work, I promise you. Excuse me. Okay, so like everything else here, let's do our comparison, or let's set up our initialization here. So my I guess we can use that up here like we did before. And I can say I signed double word, and I can put a 0 there. And then I can say, okay, move into I, 0. Okay, so now here's my comparison, right? So that's my initialization of I. So my comparison, just like before, is compare I to size. And we just have to think size is the ECX register, because we passed that along. So that, if you want to go back and change X to be EDX, and size to be ECX, and value to be EBX, you can go ahead and do that, because they're no longer, it's no longer the names, it's the registers that we're using. So just like I was saying here, like if this is the opposite of less than, is greater than or equal to. So if this is JGE, if I is greater than or equal to size, jump to can't find, because that's where I'm going to fall through a return a -1 and go again. So, okay, so does that change anything? Nope, we have an infinite loop because I have not done a lot of the other stuff I'm supposed to be doing, especially here with the increment of I. This guy right here. So, so I've done my initialization, I have done this guy here, which is my comparison, I've done my incrementing. Right now, it still returns a -1, -1, but it does an infinite loop anymore because it's tried every possible way, even though we haven't done the if statement yet. It's tried to go 7 times through this loop, and it's just not working out for us. Okay, so fair enough. All right, so coming back to this one more if statement, another comparison. So this is where things get a little jumpy here. So it doesn't, so I can't just say, I could try this. I could say comparison, okay, EDX, this is where things are fun. Like if I just say X is EDX, which is a pointer, and I go, okay, now move over size elements, move over ECX elements, and compare that to EBX. Wouldn't that be great if it could do that? That would be amazing, but oh my goodness, heck no, right? There's just a lot going on here, invalid use of registers, and there's at least 2 or 3 things going on here that I can't necessarily use. So, like, I kind of have to work my way back for this, and I go, well, what do I do? So what I could do is I could move into the EAX register. I could say move into that, my EDX, which is my offset. And then I can, oh boy, this is the fun part here. Like, let's see. Let's bring this up. Let's initialize EAX. And let's just say EAX is the pointer to the array. Okay, so let's just say, because that is the pointer to the first element, so the 2 would be stored there. So what I can do here is I can compare what's stored at EAX and compare it to what is at EBX. I believe that one will fly. So what that means is maybe I can just use EDX directly. I think I can. I don't want to screw, it's one of those things. I guess I can just say kind of like this, since I'm not going to lose the pointer per se. So I can say, okay, go to EDX, which is, in this case, it's the first element of my array. And now, just to kind of make things easier too, if it helps you out to use the D word pointer, just so you go, okay, take whatever EDX is pointing to, treat it like a double word, or take EBX, and whatever's in, and compare to this. So far so good. And so now if they're equal, if they're not equal, then I want to come around, right? Because I don't want to do anything. Not found. So I want to jump if not equal to not found. Otherwise, what I want to do is return I. So this is the case where I move the EAX, move the I into there, and then do my jump to done. And this doesn't necessarily work out. And why is that not the case? So let me see what that still returns a -1, -1. So what's happening here is that I'm testing whatever EDX is pointing to as a double word and testing that against the EBX register, which is the value I'm searching for. If they're not equal, I'm going to not found, and I'm incrementing I, and I'm trying again. But then if you notice, EDX is never modified. So that's probably where my problem is right now. I needs to be modified for sure, because that's this guy right here. But the pointer itself to move over and do stuff too, that needs to be incremented as well. And since I'm using 32-bit integers, I believe I can just take and add 4 to EDX. And lo and behold, huzzah, magic. And because of that, because every time I'm starting with the initial pointer and like the first element of the array, and because I know they're 32-bit ints, every time I'm accessing one and I need to go to the next one, I move over 4 bytes and 4 bytes and 4 bytes and 4 bytes. And so that works out for me, because that actually prints out the +5 because it finds it at element 5. And the -1 is still -1. So coming back here, if I want to try this one more time here and say just put a different number in here, instead of testing a 1, I'll put an 8 and test it out, and I get the 4, because that's element 4 in this guy over here. This is 0, 1, 2. Oh, actually no, that's not correct. Or did I not put the numbers in correctly? 2, 9, 3, 4. Okay. So what is going on? Why didn't it work, right? I feel like it did work a minute ago here. The 1 returns a +5. 0, 1, 2, 3, 4, 5. Okay. Did I just put the wrong value in? I put an 8 in. Nope. I don't know. I think I just screwed myself up. I'm just talking and thinking and doing things for the first time while I'm trying to make a video while my kid's running around upstairs. So 0, 1, 2, 3, 4. The 8 is found at 4. Oh, duh, because I'm looking for a 4. If the 4 would be at element 3. Sorry to waste your time. Hopefully you're already running through this at half double speed anyway. So yes, if I look for the 4, I will find it at 0, 1, 2, element number 3. Yes, okay, so I was correct all along. But here is the code one more time. So this is working code. And so again, it is never beneath you to write code out in C++ or Java or Python, something simple. None of those crazy languages, but something simple where you can kind of take this and now you can convert this into assembly language. And again, it's not always a one-to-one. There's always some little catches, but it works, right? And so now my final step here is, this is always what we do, is now that I have this working, everything that is not EAX, everything that is not my return value, that has been modified by my function, has to be pushed and popped. So I just have to go through here and just kind of look through and I go, what did I push in, or what did I modify? I is fine because I is a global, and that's And later on in chapter 8, we'll play around with this anyway and push this on the stack, and it'll mean nothing anyway. We'll just move this over. But let's see, I has been modified, EDX has been compared, not modified, EAX has been modified, EDX. So the only thing in this entire function that is not EAX that's actually physically modified is the EDX register, because we're moving that pointer along every time. So to make this thing, so what would happen, let me just say, and this is, I can finally give you an example of why we do this. What if I just get rid of this guy? Because you're like, oh, the EDX register is never modified by this function. And you go, okay, it worked, but did it work? Oh boy, right? So like I found the 4 at element whatever. So what if I tried to search for, 4 and then I tried to search for 2. And you're like, where are you going with this, Brad? But what's happening is, as I'm moving stuff along here, and I find the number 4 at element 3, right? 0, 1, 2, 3. And what happens is, if I don't put EDX register back, the next time I try to run the same stuff without resetting EDX, I'm trying to find the 2. The 2 is there in element 0. But it can't find it because the EDX register, because it's been modified and never put back, is searching starting here, and it's going, can't find the 2, and then it has to default and go, oh, can't find it, it's a -1. So that is why we do the pushes and the pops, so that whatever, because this is the only thing I promised to modify. And I'm allowed to modify stuff as long as I put it back when I'm done. So I'm allowed to do my push EDX here and my pop EDX right before the return. And this is part of the reason, again, why you have just one return. Because if I need to do this in 2 places and I have 6 registers, it just becomes an ungodly amount of code to do. So now running this one more time here, you see, instead of it coming up -1 like it did before, now because it put EDX back, EDX is back to its original value, the value that got sent into it. Now, because it starts at element 0, which is where the pointer is, now it finds it legitimately and finds it at +0. And so everything else is working just fine and everything else is happy. So this one might take a while to wrap your head around. I don't doubt that. But this is a great problem. If you're getting this and if you understand everything that's happening and how to set up and how to do all the jumps and the comparisons and figure out why the pushes and the pops and all of this stuff, how to do the moves to pass everything along to functions. If you get all of this information, you are good. You are ready. Chapter 7 is multiplication and division. Some of you have already been doing that, so that some of you that's not even really a step up. And then you're ready for chapter 8, because chapter 8 is we're going to take everything we've been doing and we're going to use the call stack and we're going to go nuts and we're going to change this around. So we're going to be pushing stuff on the stack instead of moving registers around and doing that kind of stuff. But again, 3 good examples here for your review. As always, if you have questions, send me a comment here on YouTube, send me a comment or an email through my email at swardb@cod.edu. And I'll be making some videos in the near future, so thanks for hanging out, and we'll see you next time.